So now that you understand conditional probability, you can understand how to apply Bayes' theorem, which is based on conditional probability. And it's a very important concept, especially if you're going in the medical field, but broadly applicable too, and you'll see why in a minute. It can tell you very quantitatively sometimes when people are misleading you with statistics. So let's see how that works. Now that you understand conditional probability, we can talk about Bayes' theorem. You hear about this a lot, but not many people really understand what it means or its significance. So let's talk about Bayes' theorem at a high level here. So Bayes' theorem is simply this. The probability of A given B is equal to the probability of A times the probability of B given A over the probability of B. All right, so you can substitute A and B whatever you want. One common example is drug testing. So we might say, what's the probability of being an actual user of a drug given that you tested positive for it? And the reason Bayes' theorem is important is that it calls out that this very much depends on both the probability of A and the probability of B. So the probability of being a drug user given that you tested positive depends very much on the base overall probability of being a drug user and the overall probability of testing positive, okay? It also means that the probability of B given A is not the same thing as the probability of A given B. So the probability of being a drug user given that you tested positive can be very different from the probability of testing positive given that you were a drug user. So, you can see where this is going. There's a very real problem where diagnostic tests in medicine or drug tests yield a lot of false positives, right? And you can still say that the probability of a test detecting a user can be very high, but it doesn't necessarily mean that the probability of being a user given that you tested positive is high. Those are two different things, and Bayes' theorem allows you to quantify that difference. So let's nail that example home a little bit more. So again, a drug test can be a common example of applying Bayes' theorem to prove a point. Even a highly accurate drug test can produce more false positives than true positives. So in our example here, we're going to come up with a drug test that can accurately identify users of a drug 99% of the time and accurately has a negative result for 99% of non-users. But only 0.3% of the overall population actually uses the drug in question. Okay, so we have a very small probability of actually being a user of a drug. What seems like a very high accuracy of 99% isn't actually high enough, right? We can work out the math. So let's let event A means that you're a user of some drug, and event B is that you tested positively for the drug using this drug test. So we need to work out the probability of testing positively overall, and we can work that out by looking at the probability of testing positive if you are a user and the probability of testing positive if you're not a user, and that works out to 22.8 it works out to 1.3% in this example. Okay, so we have probability of B, the probability of testing positively for the drug overall, without knowing anything else about you. Now, if you do the math, the probability of being a user of the drug given that you tested positively, what's the probability of a positive test result, meaning that you're actually a drug user, works out to the probability of being a user of the drug overall, which is 3%. We know that 3% of the population is a drug user, times the probability of B given A, the probability of testing positively given that you're a user. And again, this test has what sounds like a very high accuracy of 99%. So we have 0.3% of the population uses a drug times the accuracy of 99% divided by the probability of testing positively overall, which worked out to 1.3%. So the probability of being an actual user of this drug, given that you tested positively for it, is only 22.8%. Okay, so even though that this drug test is accurate 99% of the time, it's still providing a false result in most of the cases where you're testing positive, okay? People overlook this all the time. So if there's one lesson to be learned from Bayes' theorem, is to always take these sorts of things with a grain of salt. Apply Bayes' theorem to these actual problems, and you'll often find that what sounds like a high accuracy rate can actually be yielding very misleading results if you're dealing with a low overall incidence of a given problem. We see the same thing in cancer screening and other sorts of medical screening as well. It's a very real problem, and there's a lot of people getting very, very real and very unnecessary surgery as a result of not understanding Bayes' theorem. So if you're going into the medical profession with big data, please, please, please remember this lecture. So that's Bayes' theorem. Always remember that the probability of something given something else is not the same thing as the other way around. And it actually depends a lot on the base probabilities of both of those two things that you're measuring. So the probability of a drug test being accurate depends a lot on the overall probability of being a drug user in the population, not just the accuracy of the test. Very important thing to keep in mind, and always look at your results with that in mind. Bayes' theorem gives you the tools to quantify that effect. Hope it proves useful.